Alrighty guys, welcome back. Today we are going to be doing pedigrees. So we're moving on from Punnett squares just for a little bit, and then we'll go back to dihybrid crosses. If you're wondering why I'm dressed in a hoodie, it's because it's Red Ribbon Week and we got to wear comfy clothes today because it's actually pajama day. So we have a few assignments that we're going to do as a group. So you should be in Monday. And there was nothing for you to actually turn in. Today is just a day for me to go through and refresh your memory on things that you would have done in biology. And if you don't remember, it's kind of like learning it for the first time. But these things are really not that difficult. So we have 2 assignments today that I'm going to do with you, and then 1 assignment tomorrow. Then you'll be doing an assignment on your own for the second half of class on Tuesday and for Wednesday's remote day. And then we'll probably move on to dihybrid Punnett squares Thursday and Friday. So I'm just going to start off by telling you a little bit about what pedigrees tell you. And it's all about family tracing. So you can look back and see who had certain characteristics and what are the likelihood that they will show up later on. You can have dominant pedigrees or recessive pedigrees, and we can have autosomal traits on them, or we can have sex-linked traits. So this particular pedigree is for Huntington's disease. When you're looking at a pedigree, anytime you see a shape that is completely filled in, that means that the person has that disorder, or they are affected with the disorder. So it shows you here that the circles that are filled in and the squares that are filled in will have Huntington's disease. And on here there's there's 4 different people who have it, and it's a mix of both. There's 5 people, if I could count correctly, but it's a mix of both males and females. Now, Huntington's disease is actually an autosomal disorder, so it affects males and females at the same. It doesn't matter as far as sex goes. Whenever you have a square, that's going to be a male. Circles are going to be females. If they are not filled in, then that means that they do not have the disease or they don't exhibit the disease. If you have a horizontal line, that means that 2 people are married. Vertical lines are going to represent their children. And then you can see who their kids marry or if they are single for now. And you can see even down here they have grandkids. So it's showing us 3 different generations. And it starts with the oldest generation at the top and it works down to the newest or youngest generation. So let's start with question number 1, and this will kind of help you guys to understand how pedigrees work. Which members of the family above are affected with Huntington's disease? Now, if you notice, they are numbered. Family members are numbered, and then we have the generation down the side. So I'm going to say that in generation 1, family member number 1 is affected. Now, I could say great-grandfather, but then you start getting into nitpicking with which sister has it or which daughter has it. It's just too much. So it's easier to go based off the generation and number them. And if they are not numbered on your paper, you can number them yourself. In generation 2, we are going to have individuals numbers 2, 3, and 7 are going to have it. And then in generation 3, we just have number 3 who's affected. There are no carriers for Huntington's disease. You either have it or you don't. With this in mind, is Huntington's disease caused by a dominant or a recessive trait? So if you either have it or you don't, that means that you only need 1 allele in order to exhibit this disease. So that would make this a dominant trait. If it was a recessive trait, you would have carriers. And a carrier is somebody who has 1 recessive allele and 1 dominant allele, so they can pass the trait on, but they themselves don't actually have it. How many children did individuals in generation 1 have? So my individuals are 1 and 2, generation 1. They had 1, 2, 3, 4, 5. They had 6 children. The people with the horizontal lines, they married into the family. How many girls did generation 2, individuals 1 and individuals 2 have. So we're just looking for girls. That means that we're looking for the circles. So here's generation 2, individuals 1 and 2. They had 2 girls. And how many have it? Just 1. Individual number 3 has it. How are individuals in generation number 3, 2, so we're talking about this person here, and generation 2, number 4. How are they related? So this is their mother and father. So this would be an uncle. It's a male. How about individual in generation 1, number 2? So we're talking about this person here, and generation 3, person number 5. So here's the parents. Those are going to be the grandparents. So I could say grandmother. And that would be grandson. And I guess I could go back over here and put uncle and niece. Oh, and niece. Well, you get the idea. Uncle and niece. All right, we can move on down to number 6. There are 11, and we're going to use this pedigree. Pedigree to the right shows a family's pedigree for hitchhiker's thumb. Is this trait dominant or recessive, and how do you know? Hitchhiker's thumb just means that your thumb bends back a little bit farther whenever you're holding it straight up. And that's how it is naturally. It's not saying that you can bend your thumb back, it's saying that naturally it has a bend in it. So if we're looking, we only have 2 individuals out of this entire pedigree that have that trait. And we have 4 generations here. Nobody in 3, 2, or 1 has it, but it did show up in generation 4. So looking at that, I would say that this particular trait is going to be recessive. I am spelling things terribly today. Jeez. And how do I know that? Recessive traits tend to at least skip 1 generation. In this case, it skips 3 generations. And a good rule to follow is if kids have it but the parents don't have it, it has to be a recessive trait. Otherwise, one of the parents would have exhibited it. But in this case, each parent had a recessive allele, so they were carriers for the trait, meaning they weren't affected themselves, but they were able to pass it on to their kids. How are individuals in generation 3, number 1? So they started over here. Normally you would start here with 1, 2, 3 and go across, but so we're looking at this girl here, and individuals 3, 2. How are they related? Well, they're married. They're husband and wife. And now, sometimes things get a little sketchy when you're reading pedigrees, just because of how they are made. So if we were to look at their parents, we would see that the father of this girl and the mother of the boy, they are actually going to be brother and sister. So that would actually make these 2 cousins, which is a little bit different. So they're husband and wife, they're also cousins. Maybe they're not close cousins. Moving on. How would you name the 2 individuals that have hitchhiker's thumb? Again, they numbered this one a little bit off, but we're just going to follow how they numbered it. Normally you would start with the first one as 1, but we would say they are generation 4, individuals 1 and 3. Name the two individuals that were carriers of Hitchhiker's Thumb. Now, there could be more individuals that are carriers of it, but in this case, we only know that two people definitely have it, so we're going to go up to their parents, and that means that this girl could be shaded halfway in. This boy could also be shaded halfway in. Some pedigrees will label them for you, some will not. They leave it to you to figure out. So those two individuals are definitely carriers. So we're going to be in generation 3, and it's going to be individuals 1 and 2. Is it possible for individual 4, generation 4, number 2, to be a carrier? Is it possible? Yes. We don't know because it's not halfway shaded in, so they didn't give us that information. But they could have received one recessive allele. They could have one. Because that's all you need in order to be a carrier of something. But it is important to note that it is a recessive allele. If they had a dominant allele, they wouldn't be carrier. The pedigree to the right shows a family's pedigree for colorblindness, which sex can be carriers of colorblindness and not have it. So this one, they did show you which ones were carriers by looking at the half shading. Anytime you see a half shaded object or shape, that means that they are a carrier. They don't exhibit it, but they can pass it on to their kids. So if we're looking, there's only one sex that can be carriers, and that's going to be the females. So we would say that this trait is an X-linked trait. If it was Y-linked, it would still only affect the boys, but X-linked traits make girls carriers because they could have one allele that's affected and one allele that is not affected. Why does individual 4-7 have color blindness? 4-7. So here's 4. So we're talking about this person right here. Now it's a girl, and it is rare for girls to be colorblind, but it can happen. Obviously, it did here. So why does she have it? Well, her dad had that affected X, so he could only give her an affected X, and her mother was a carrier. So she had a 50-50 shot of getting a good X or an affected one. Her mom gave her the affected one. So I would say mom is a carrier, and dad has it. Nothing he could do. Why do all the daughters in generation 2 carry the colorblind gene? So looking up here, generation 2, we're going to go up to generation 1 here. It's because dad has it. So dad is giving them that affected allele. And since his other sex chromosome is a Y, he can only give them the affected X. Name 2 4th generation colorblind males. It's individuals 1 and individual 5. Okay, hold on one second here. Okay, so we are moving on with our pedigrees here. A pedigree is a chart of a person's ancestors that is used to analyze genetic inheritance of certain traits, especially diseases. The symbols used for a pedigree, we've already went through these. Circles are females, blank is unaffected, filled in as affected, same for males who are squares. Siblings are placed in birth order from left to right and are labeled with numbers. These ones are labeled correctly, whereas the other ones were not. You always start with 1 being the very first individual. And the generation is going to be labeled with a Roman numeral. There's only a few questions on this one here. Try to identify the genotypes of the following individuals using the pedigree above: homozygous dominant, homozygous recessive, or heterozygous. So first, right off the bat, as we look at this, we need to determine if the traits are going to be dominant or if it's a recessive one. So it skips a generation completely here. That's telling me that this is probably a recessive pedigree. So we're looking for individual generation 3, number 3. So this person right here. So because it does skip that generation, that means that this person has to be homozygous recessive. And there I go again with my terrible spelling. Homozygous recessive. Individual in generation 2, number 1. So we got to go up and look at the parents. We know that they don't have it, so that means they have at least one dominant allele, but dad does have it, so that means they're going to be heterozygous. Individual 1, number 1, this person right up here, they're homozygous recessive. And individual generation 2, number 4. So we know that they have at least one dominant allele. If we go up to their parents, the parents are both clear of the disorder, so we know that they don't have it. We can then go down and look at the kids. So it's not just simply looking at that person and saying this is what they are. You have to look all around them. Now, they got married and they had 5 kids. 2 of those kids ended up with the disorder. So since it is recessive, that tells me that they would have had to get one recessive allele from the mom, one recessive allele from the dad, which would make them heterozygous. So they were a carrier for the disorder. Is this trait dominant or recessive? It is going to be recessive. And that's because it skips a generation. I could also say unaffected parents have children who are affected. So that is another telltale sign of a disorder being recessive, is if you look at the parents and they're free and clear, but the kids have it. How can you know for sure that individuals in generation 2 and individuals 2, numbers 3 and 4, generation 2, individuals 3 and 4 are heterozygous? I know for sure that they are both heterozygous because they have a kid with it. They have children who are affected. And then this last one here, I believe is a drawing. So brown eyes are a dominant eye color allele and blue eyes are recessive. A brown-eyed woman whose father had blue eyes and whose mother had brown eyes marries a brown-eyed man whose parents are also brown-eyed. They have a son who is blue-eyed. Please draw a pedigree showing all 4 grandparents. The 2 parents and the son indicate which individuals you are certain of their genotypes and where there are more than one possibilities. Okay. So we have, well, they have a son. I might start, let's see, at the bottom here. They have a blue-eyed son. So there's the son. And then we know that we have the dad and the mom. And we got to get their parents in here. And there is no really right or wrong way to draw one of these pedigrees. I tend to put my women, I guess, on the right and the boys on the left, but I could have swapped it and did women on the left, boys on the right. What is important is how you label things. So, a brown-eyed woman whose father had blue eyes. So he has blue eyes. So I'm going to label him with 2 little b's because I know that his genotype is recessive. Wait a second. We're talking about the woman right now. Brown-eyed woman. So here's my brown-eyed woman, whose father had blue eyes. So we know that she had one capital B, Daddy had two blue eyes. Her mother had brown eyes. We don't know what the mother was, but we know that the daughter is certainly going to be heterozygous because Dad had to give her one of those recessive alleles. So Mom could either be two capital Bs or she could be heterozygous like her daughter. Marries a man whose parents are also brown-eyed. Brown-eyed woman whose father had blue eyes and whose mother had brown eyes marries a brown-eyed man. So we know that he has this one capital B, whose parents are also brown-eyed. So the parents also have at least one capital B. They have a blue-eyed son. So if the little boy down here is blue-eyed, that means that the dad also had to be heterozygous like the mother. And in order for this to work, one of these parents also had to be heterozygous. So it could have been Dad, or he could have been the homozygous dominant one, or it could have been the mom. Or they both could have been heterozygous. So that would be how we would draw up that Punnett square. Or pedigree, rather, sorry. Okay, I'm going to stop this video here because I realized that we've hit 20 minutes.